Hello everyone, my name is Joshua Walter. I'm a mechanical engineering student and I've been working under the direction of Dr. Chongze Hu in the Department of Aerospace Engineering and Mechanics. And my project is atomistic simulations of interfacial segregation in multi-component vanadium alloys. So first off, a little background. So when almost all materials, all metals, when they solidify, they do not solidify uniformly. Different crystalline structures start forming at different points throughout the material, and eventually, as the material continues to solidify, these crystalline structures will meet up. And where they meet up at different angles and orientations. These locations where they meet up are sites of lots of disorder, and they are called grain boundaries. And since these sites have a lot of disorder, they can have some unique material properties, which is why they are useful for studying. So in many multi-component alloys, many alloys that are more traditional, where you have one primary element, and then the alloy is doped with a little bit of another element or two. In these types of alloys, oftentimes there tends to be grain boundary segregation. Certain elements, certain of the doped elements, tend to segregate and move to the grain boundary. And they do this because these doping elements tend to be different sizes than the atoms in the bulk. Because of this, these create disorder throughout the bulk, leading to higher energy in the system. So, in order to lower the overall energy of the system and create the most stable structure, these atoms will want to segregate to the grain boundary, where there's already a lot of disorder, therefore lowering the total energy of the system. And this segregation can alter the properties of the grain boundaries, and in turn, the properties of the material. So for our research in particular, we are studying vanadium alloys. And vanadium alloys tend to have a lot of uses, but one of their primary uses is in nuclear applications. The reason for this is due to their high temperature strength and radiation resistance. Vanadium alloys tend to be very low activation, so they don't have negative interactions with radiation, and making them great candidates for these uses. However, they do have some weaknesses. For example, at high temperatures, some vanadium alloys will tend to have poor creep performance after being under load for long periods of time. Eventually, the material will start to weaken. Obviously, this is not ideal, so we're working to develop better vanadium alloys that will perform better under these sorts of situations. And then we're also working just in general to understand how grain boundaries can affect material properties. So for our project, we're doing mostly all computational work right now. So our first goal is to create a large database of vanadium alloy behavior. We're studying, in particular, the vanadium, titanium, tantalum system. We'll vary the composition of the titanium and tantalum from 0.5% to 4% respectively, giving us a total of 64 different compositions to study. And then we study these compositions at different temperatures. We're studying the sigma 5 grain boundary currently. This is a very ordered grain boundary. And then to do our work, we're running molecular dynamics Monte Carlo simulations, and then studying these material properties. So for our tools, the first important tool we need is a symmetric grain boundary generator. This is what allows us to create our actual structure file that we can then use for our simulation. Then we also need to use high performance computing. These simulations we're running will take a lot of time. Even using the HPC, these simulations will take at minimum half a day or even longer to run. Then we're using large-scale atomic molecular massively parallel simulator, or LAMMPS code. And this is what controls the behavior of the atoms there's interatomic potentials that control how the atoms will interact with each other, what type of forces they'll experience. And this allows us to model the atomic behavior inside our grain boundary structure file. So the first step in our methodology then, after we have our structure file, is our equilibration. So we'll take our basic structure file and then essentially relax the structure. This is run at low temp, and we're basically trying to minimize the forces that these atoms are experiencing. We're just trying to find the most stable energy and temperature so that when we actually run our molecular dynamics simulation, there won't be any errors, any other sorts of forces that may affect our results. So after we've equilibrated our structure, then we can do our actual atomistic simulation. So to do this, we'll dope our vanadium grain boundary structure with small amounts of titanium and tantalum, and these elements will replace the vanadium atoms randomly throughout the grain boundary structure. And then after that, the interatomic forces, interatomic potentials I was talking about are used to calculate these forces and where the atoms want to go, where they would like to be inside this grain boundary structure. And then if that makes sense, the atom position will be updated, and then this will repeat many times until the most natural state for the structure has been achieved and atomic segregation and diffusion has been simulated. So here's a little example of an illustrative simulation result. As you can see, at first, the elements are dispersed at random throughout the structure, and then after the simulations run, as you can see, there's a grain boundary in the very center of that structure file, and as you can see, tantalum tended to segregate there. So overall, we found in our results that the grain boundaries tended to prefer tantalum enrichment. Titanium generally did not segregate to the grain boundary. However, increased titanium concentration did encourage some tantalum segregation. We also found that higher temperature did slightly discourage segregation, which is an expected result, as higher temperature means more energy in the system, so the differences between the atoms is less important at that stage. So for our future work, one of the first and most important things we'll do is continue to analyze our current simulations. We're developing some code to quantitatively analyze these results and where the atoms tend to segregate. After that, we're going to run some simulations on other sorts of grain boundaries, other grain boundary types. Then we'll conduct simulations to evaluate properties, material properties such as strength. And then eventually down the road, we're going to be working with another lab to create our best performing alloy and conduct some physical experimental tests. Does anyone have any questions?
You mentioned the simulations. So is that software that you all build in-house, or is it some external software, or where did all that come from? And after that, when the question was, you said you'd take like half a day to run it. How often are you running these simulations?
So to answer your first question, these software packages, almost all of them are open source, things that other labs have developed, and then we use them for our purposes. And then for your second question, could you repeat it, please? Sorry.
How you mentioned it would take half a day sometimes to run the simulations. So how frequently are you doing the simulations?
So we try to have as many simulations as we can be running effectively. We're not the only lab using these high-performance computing tools, so sometimes we do have to wait, but we try to run many of them weekly.
How accurate are these simulations in predicting real alloys and experimental results?
So in general, they do tend to be fairly reasonable, fairly accurate. There was a lot of data analysis and experimental results that went into creating these sorts of software. However, at the end of the day, this is an idealized simulation, so it's never going to be able to perfectly predict experimental results, but it's a very good starting point that then experimental results and experimental tests can be based off of.
How does the grain boundary segregation affect mechanical properties?
So grain boundary segregation can affect the properties in a few different ways. For example, for strength, grain boundaries tend to be areas of weakness in a material. Things like cracks can propagate along them. However, with different elements occupying the grain boundary, they can affect the properties because, for example, these elements might be different sizes, have stronger bonds, things like that. And that can either positively or negatively affect the properties such as strength.
Why did you choose the sigma 5 grain boundary to study?
So we chose the sigma 5 grain boundary, first off because it's a good, realistic grain boundary to run, but then it's very computationally easy to conduct simulations on because it's very symmetric. That also means that there's a lot of previous research that's been run on the sigma 5 grain boundary, so we can accurately predict, we can have more results to compare ours to, so it's a very good starting point for our research.